This is part 3 of lesson 2, creating your first application of LabVIEW Core 1 training. Please make sure you have watched all previous parts before watching this part 3 of lesson 2. Okay, in our second part we discussed mechanical actions of Boolean controls. Now we are discussing numeric data representation. So let's start.
After completing this module, Numeric Data Representations, you will be able to select the appropriate numeric data representation for your application.
Yes, it is very important that you should select correct numeric data representation for your application for your condition.
Your requirements for numeric data will vary depending upon your application. To ensure that your VI functions effectively and efficiently, it is important to select the appropriate format for your numeric data. In LabVIEW, we call these formats representations.
Yes, if you do not select proper numeric data, then you can lose your resources. You can lose more memory. To save your resources, you should select appropriate data type.
LabVIEW represents numeric data as floating point numbers, fixed point numbers, integers, unsigned integers, and complex numbers. Numeric data types differ in two ways: the number of bits they use to store data and the data values they represent.
So yes, you can represent these floating point numbers in LabVIEW, also integer numbers as shown, also complex numbers and floating point, and also you can represent any real value numbers as well.
Choosing the numeric representation of a control, indicator, or constant is easy in LabVIEW. Simply right-click on the object, select Representation, and choose the numeric representation that best fits the range and precision requirements of your data.
Okay. Like right-click the numeric control, go to representation, and these are the different numeric data representations from where you can select appropriate numeric data representation as per your application and need.
Before we examine each numeric representation, let's look at how LabVIEW stores data. LabVIEW stores data in memory for controls, indicators, wires, and other objects depending on the data type of the object. For each numeric object, LabVIEW allocates an area of memory that is at least 8 bits wide. Depending on the required range and precision of the data object, the area of memory that is allocated can range from 8 bits to 128 bits wide. Certain bits in this memory allocation are defined by LabVIEW to store specific elements that comprise the number, such as the fractional portion of the number and its sign, whether the number is positive or negative. An unsigned integer is any whole number greater than or equal to 0. In LabVIEW, unsigned integers may be 8, 16, 32, or 64 bits wide. The bit width provides for the required range of possible numeric values. Click on each numeric representation to learn more about it.
Okay, these unsigned integers are positive numbers, so it can be 8-bit, 16-bit, 32-bit, or 64-bit. So for the range for unsigned 8-bit is 0 to 255 as per formula of 2 power n, where n is 8-bit here. So it will be 2 power n minus 1, 2 power 8 minus 2 power n minus 1, which will be 255. Similarly, the range for U16 will be 2 power 8. Actually, 2 power 8 will be 2 power 16. 2 power 16 minus 1. So it will be 0 to 65,535. Similarly, this is 32-bit long number, unsigned, and its range is 2 power 32 minus 1. Similarly, this is U64, 64-bit long number. It is unsigned integer.
Signed integers are similar to unsigned integers except that they can be positive or negative. The most significant bit determines the sign of the number. Because of this, the absolute range of a signed integer is half that of its unsigned counterpart, but the total range is just as wide.
Like this is I8, this is signed integer. It can represent positive and negative both numbers. It is 8-bit I8, and it will have the range as per the formula of minus 2 power n minus 1. So minus 2 power n minus 1, which will be 7, which will be minus 128, to 2 power n minus 1 minus 1, which is 127. This is I16, 16-bit uh, signed number, and it has range up to minus 32,768 to 32,767. Similarly, this is 32-bit long signed number, this is 64-bit signed integer, and this is its range. So signed represents both positive and negative numbers, unsigned only represents positive numbers.
Fractional numbers are represented by multiple floating point formats. Floating point numbers have a very broad range and degree of precision. Double precision is the default format for numeric objects. For most situations, use double precision floating point numbers. Use single precision floating point numbers when memory savings are important and you will not overflow the range of the numbers. Use extended precision floating point numbers only when necessary, because performance of extended precision arithmetic can vary depending on the platform.
So this is floating point number, double precision floating point, range is shown. This is floating point number, single precision, 32-bit, and range is shown. And this is floating point number, extended precision floating point number, and range is shown.
In addition to signed and unsigned integers and floating point numbers, LabVIEW also supports fixed point and complex numbers. For more information on these formats, refer to LabVIEW Help. It is possible in LabVIEW to wire an object of one numeric representation to an object of another representation. LabVIEW automatically converts from one data format to another. This is called coercion. LabVIEW coerces to the data type that does not result in fractional data loss. In this example, when adding a double precision floating point numeric to a long integer, LabVIEW coerces the long integer to a double precision floating point numeric and then adds the two values together. If both data types are integers, LabVIEW coerces the data type with the lower maximum value to the data type with the higher maximum value. In this example, LabVIEW coerces the signed integer to an unsigned integer. Because LabVIEW attempts to coerce a negative value to a data type that does not support negative values, the function generates a value of 65,531 instead of -5. LabVIEW places a coercion dot on the block diagram node to alert you that the value passed into the node has been coerced to a different representation. In certain coercions, coercion dots may lead to an increase in memory usage and execution time, and a decrease in accuracy. In the case of the previous example, coercion resulted in very inaccurate data that could impact the effectiveness of your application.
Yes, coercion is a very important concept in LabVIEW. Coercion occurs when you try to when you try to perform operation on different numeric data representation. Like you are adding two different numeric data representation here. One is floating, another is the integer. So certainly there will be the coercion dot, and this coercion dot shows that this I32 is first converted into DBL, and then the addition operation is performed. Like here, two integer numbers are added. One is the signed 16-bit, another is the unsigned 16-bit. So signed 16-bit will be first converted into unsigned 16-bit, and then the addition operation will be performed. But this will result into a wrong answer, because -10 is a negative number. If I16 is converted to U16, that number will be positive. So therefore, you will get a wrong number. So there are two main drawbacks of coercion. One is that it has it takes a lot of uh, it takes more resources, and it takes more consumption. And the second is the results can be wrong, and the results can be incorrect because of the coercion issue. Therefore, it is very important to avoid coercion when you are performing operations in LabVIEW. So coercion must be avoided uh, in LabVIEW.
To eliminate coercion dots, match the output data type of the control or constant to the data type of the receiving terminal. Sometimes, though, it's simply not possible to select like representations for objects and terminals. In those cases, the best solution is to use numeric conversion functions.
Yes, in order to get right answer, what is done right now here, this U16 is first converted into I16 to match these both numeric data representation. If now these both numeric data representations will be matched, then this coercion dot will be avoided, and it must be avoided. And now you are getting the right answer. Minus 10 plus 5 will be minus 5. So let me show you the palette over here. Now you see, here is the, when you go to right click on block diagram in numeric, in conversion, this is the conversion subpalette where you can convert the data types to match them in order to avoid the coercion. All right, and coercion must be avoided.
Select the appropriate data type, then click Submit.
Okay, which is the most appropriate numeric data type for a control that determines the number of samples to take on an analog input channel? Certainly, samples will be integer number. They won't be the floating point number. So this is assigned integer is the right option. Submit it. Yes, that's correct. Only a whole number of samples can be taken. Selecting a float point representation will result in a coercion dot. Exactly. Continue. Okay, which option is best solution to resolve the coercion in the following VI? Okay, both options can be right. You can select any of the option. Both in both ways you can avoid the coercion. So yes, using a numeric conversion function on one input, either the solution will resolve the coercion issue. So you can select either the solution. All right.
You've completed this module. Here is a summary of what you've learned.
Okay, you have learned that numeric data in LabVIEW may be represented in one of the 15 possible formats. There are different formats for the numeric data representations. And the other thing you learned that LabVIEW supports signed and unsigned integers as well as floating point numbers, fixed point numbers, and complex numbers. And it is very important choosing the appropriate format. Range and precision of numeric data type is very important and can impact the effectiveness and efficiency of your application. When you will study in advanced course LabVIEW FPGA, to access the FPGA using LabVIEW, there you will realize that it is very important to select appropriate numeric data in order to save the FPGA resources. So it is always important to select appropriate data type. If you need only U8, if your work can be performed with U8 unsigned 8-bit number, then taking U64 is a wrong decision, and it can lead to more resources utilization, and it should be avoided. Appropriate data type should be selected. LabVIEW automatically converts or coerces mismatched numeric data types. Yes, it converts, but then it shows coercion dot. We should try to avoid coercion. Coercion should be avoided by choosing the data representation carefully or by using the conversion functions. As I showed you the conversion subpalette, use that conversion subpalette in order to avoid the coercion dot. All right. Okay. Strings. Strings is a sequence of displayable or non-displayable ASCII characters. Strings provide a platform-independent format for information and data. Some of the more common applications of strings include creating simple text messages, controlling instruments with text commands, storing numeric data to disk to store numeric data in an ASCII file, first convert data to strings, instructing or prompting with dialog boxes. So previously we have also studied that there are three data types majorly used: string, boolean, and numeric. So string is when you want to enter some ASCII characters, and there are four formats to be followed. Display, there can be four display types. One is the normal display. This is the normal display. Another is the backslash quotes display. This is the backslash quote display. Third is the password display. This is the password display. This is the hex display. Display the ASCII values of each character in hex instead of character itself. So you can select any of the display format as per your need in a string data type. All right. Okay, now we are going to discuss enum. Enum is a very important concept and has a lot of application when designing your LabVIEW block diagram codes. So let's discuss enum right now. Okay, I am demonstrating how to create a enum. For this, I am creating a new VI. This is my new VI. I press Ctrl T to get both front panel and block diagram left and right. Okay, how can you create an enum? Right click on the front panel and go to this ring in enum palette, and from there select enum silver. This is the enum. And how do you create enum? Go right click it, go to edit items, and here you can enter the values, strings that you are interested to. Basically, what is the concept of enum? Enum give users a list of items from which to select. Enums are useful because they make strings equivalent to number. Basically, you give strings and that string data is converted to equivalent numbers, which are easy to manipulate on the block diagram. Yes, numbers are easy to manipulate on the block diagram as compared to integers. Each atom represents a pair of values, a string value and 16-bit integer number. Now let us say you want to create a program in which you want to give the facility to user to enter different temperature units. Either it can be Fahrenheit, it can be Celsius or Kelvin. So for this purpose, you create one enum. How do you create one enum? I again repeat. You right click here, you go to ring in enum and you select enum silver. From here you go to edit items. Now say suppose you want to create an enum showing three items to the user that are basically units of the temperature. One is the Fahrenheit, another is the unit is the Celsius, the third is the Kelvin. All right. So you see that user has a list of items, three items here: Fahrenheit, Celsius, and Kelvin. User can select any of the atom. Now you see that each items represent a pair of value, a string value and 16-bit integer. This is a string value, this is 16-bit integer. Okay, when you click OK, now you see there are three options. When you click, user has the option to select any of the three items. In this way, enums are created in LabVIEW. Alright. Furthermore, again go to edit items, and then you can also move up, move down your enums. Alright. Say suppose I want to move it down. Now see, Fahrenheit is moved down. Say suppose I want to move it further down. Now it will be last Fahrenheit. Say suppose if you want to move this up, you can move up. So you can rearrange the uh, enum entries as well. Alright. And you can also disable any atom if you want to disable. Alright. And you can again enable as well. Okay. Click. Alright. So You should be clear now that enums gives users a list of items from which to select, and enums make strings equivalent to numbers, and numbers are easier than strings to manipulate on the block diagram. So this is the beauty of the enum, and we will use enums in our future applications. All right, we will discuss our next topic, tools for programming, cleaning, and organizing your VI in our next part. And before this, I want to quickly mention that there are also some other data types like dynamic. This stores information generated or acquired by an express VI. Other is the path. This stores the location of a file or a directory, and the other data type is waveform. This carries the data, start time, and DT of a waveform. In our next part, we will discuss tools for programming, cleaning, and organizing your VI. Thank you very much.